Greetings. This is Graham Warren working with you on the AnyLogic model for the Antico Cafe Greco case. So we have the model in front of us here. Just a note about how you load this model. What I suggest doing is downloading the model from the case study locally to your drive, open up AnyLogic, and then go in and open the file from wherever you saved it locally. The model has a .alp suffix, and for some reason it doesn't, the operating systems do not seem to recognize it very well. So to make sure that it does launch appropriately, don't try and launch it from within, Google or something. Put it on your drive and follow the procedure I've just recommended. All right, so I want to outline in this clip how this model works, and then we will do a separate clip on trying to validate some of the analysis that we saw previously. So the model itself lives primarily here. You can see there's a series of models here, and here is ACG. The case does change every term, so expect to see significant differences between what you have here and any reports from the past. And the main things to note here would be main, which is this screen here. And there's some, various objects that have been put on this palette here that pull out the model. And the other key one is simulation main. Now, if I click on this simulation main, you'll see that I get a series of, some properties here. And simulation main is important because you're going to be using this to change parameters of this Antico Cafe analysis that you want to do. But let's hold off on that for just a moment and figure out how this is going to look. So I'm going to just set this up for a moment so that it has the base case. I think we're good. Yep. All right, so these are the models. You also have a palette here. If this is the first time you're seeing AnyLogic, there's a bunch of built-in tools or modeling objects that are available here. Much of what we're doing is we're using. Let's see if I can open this up a tad. Here, there it is. So we're using the so-called process modeling library primarily. And we have some elements, some agent elements in here. So there's a couple of resource pools in particular. And our resource pools, there's going to be one for our Venus Arduino's bars, our VAVs, and another for the automatic machines that are present in the base case, the Juras. Okay. So let me just try and lay out for you the workflow here. So we generate customer arrivals. Then we start a stopwatch on each arrival as it comes through here. That's the meaning of this little time start. Then we try and grab a coffee maker, basically a coffee bar, either a Jura or a VAV, and then the coffee is made. So when we grab the VAV or the Jura, we're essentially grabbing a barista also. So when I refer to a VAV or a Jura here, I'm really referring to that pair of the machine and the barista. Making the coffee, after we make the coffee, then we release the VAV and the barista pair. So then they become available for subsequent orders. We click our stopwatch, and then we throw away the order. Okay, it's done, right? It's been delivered to the person, they consume, they leave. We don't worry about how long they stay. What we're interested in is the process from receipt of order to delivery of order, because we think this is highly impactful of you've got a caffeine-free state, then you've got a caffeinated or starting to caffeinate state. And this is the key part of the CX. All right, so let's walk through these blocks. So they're available on a drag and drop basis from this palette, the processing modeling palette. So you can see this here is a source, and I just dragged and dropped it here. And the each of these middle modeling blocks or objects has some properties, which you can review here. Let's have a look at this one. There are some idiosyncrasies that are captured here. So this one is expressed as an arrival rate per hour. Excuse me. This one is called customer arrivals. Okay, and the arrivals are defined by a rate. Now, interestingly, if you specify a rate, it's understood that these arrivals are according to a Poisson process. You get to specify the intensity. Now, I could have plugged in here 22.43, 19.65, whatever, 157. But I want to make this sort of a flexible modeling tool. So I'm going to create a parameter called arrival rate, which you're going to get to specify. You can adjust just like you saw the adjustments on the calculator. You want to be able to change this arrival rate, rerun the model, and get the assessed utilizations, waiting times, and the like. I also noticed that I've limited the number of arrivals here to 50,000. That is because I'm working on a free version of the software. It is capped at 50,000 to ensure that large scale models are not run free of charge, on the trial account. What else? Yeah, and I've got a customer type here, an agent type here called a customer. And you can see that I've got customers coming in here. There's another kind of agent here that we will see in just a moment. Now, this piece here is just an animation. The main modeling action actually is captured here. This is just sort of a view of what goes on the in the model. Right, so the folks come in here at the rate of whatever the rate specified is. You can see that click the timer on, and I just record the entry time for the agent, and it's a customer type agent. And then I'm going to grab a server. All right, now it's that VAV barista pair, or Jura barista pair. See, I've got two possibilities here. And what I have got is I just grab one or the other. So it's going to try and grab a VAV first, and then a Jira. You could switch those around and see if it makes a difference to your simulation, but I don't think you need to change the model at all. I think it's just a case of changing parameters, coming up with scenarios and ideas for how you want to manage this cafe, analyzing it, and then reaching a conclusion. So I have I'm allowing maximum capacity here, and I'm attaching the resource, which is going to be either a VAV or a Jura. So let's have a look at these resource pools. So the VAVs here are a type of agent in our simulation, and they're Venus Arduinos here. You can see this little sort of red icon indicates that it's an agent of some kind, and we're calling them Venus Arduinos. And the number of Venus Arduinos is number VAVs. And you can see, again, you're going to be able to specify how many you've got. So in the base case, you've got essentially 7, right? Depending on which scenario you're viewing. But there are 7 baristas. One of the things that we could not easily do in the queuing analysis was to entertain this possibility that we have, let's say, 4 Juras and 3 VAVs. The VAVs are expensive, but they are, maybe a better fit for the historical ambiance of the location. So you have slightly more modeling flexibility here because you're able to entertain a mixture of VAVs and Juras. By changing these, you can put in any number you want, like 5 and 10 or whatever, but it's available to you. So same thing with the Juras. This one here is a Jura type agent, and then the number specified on your number Juras. Right, so you've got your orders come in. You either grab the orders grabbed a barista and VAV or barista and Jura. We head on to making the coffee, and the coffee making process is laid out here. So I want to just show you this. It's called Make Coffee, and it's gonna ask, is a VAV involved? If the VAV is not involved, then it's going to assume that the service time has a mean of whatever the mean service time is, which is laid out here. So that's 150 seconds. And the standard service time of the jurors. So that's if it's not a VAV, that's if the customer doesn't have a VAV resource attached to it. And if it does, then it's going to take the mean service time and the standard deviation of the VAVs. Okay, so you've got these two standard deviations. So the one for the jurors is 5 seconds, but the one for the VAVs changes, right? If trained baristas are operating that, then it's 11 seconds. If they have just the basic training, then it's 30 seconds. So that's the difference there is the advanced training. All right, so now they've made the coffee. The delay is normally distributed with that mean and standard deviation. Now, just an interesting note here. You'll see that there's two parameters, 0 and infinity, in either of these cases. So whether or not you've got a Jura or a VAV, you're having sort of a curtailed or truncated normal distribution. I want to just explain this for a moment. We can annotate this. So the normal distribution would set something like this. You've got the mean here and whatever standard deviation you've got. Now, the problem here is that we're dealing with times, right? This is a service time, so we cannot entertain negative values. So what I'm doing is I'm actually cutting this off. And the distribution actually looks like this. It's got a full tail on the left, but it's truncated on the right. Now, because the mean service time is 150 and the standard deviation in the worst case is 30, that means that 0 is 5 standard deviations below the mean. So you're not going to get too many times that are truncated here, but there could be some. So in some sense, this is a heuristic approximation, but I was forced into this move here to keep the times non-negative. Okay, so just a small concession to making this model work. And I've also assumed that the service times are normal. We don't know that for a fact. Just assuming that we were given a mean and a standard deviation. This is as close as I can get to. I have to do something, and I chose to go with a normal distribution. Other distributional choices could be possible. So I just move on. All right, so we've now got to the point here where coffee is made. We're going to release, and now those resource pool items are going to go back. So we release all resources seized to the given seize blocks. So they get released back here, and now they're available for the next customer. We click the stopwatch. Just want to show you what that looks like. That records the end. And we're going to build a histogram on these times. So the timer starts here and ends here. And you can see how I connect these two blocks where you can see this one here identifies where the stopwatch has started. And, I guess we could add 1,000, why not? Even more, to, let's say 5,000, larger data sets. So I was basically figuring statistics on just the last 100, which is not the greatest idea. All right, so we've got some parameters here. These reflect in our, I go back to my project modeling piece here, and my project panel here. Click on the simulation main. You can see we're going to be adjusting them here under simulation main. And we've got some statistics. Well, we've got some statistics here. The queue length, this is, just show you this block. So this here grabs from the C server block. It tracks the queue length, okay? Dot size shows the size of the queue. And these two get the utilization from VAVs and jurors, okay? So that's the purpose behind those two. This is a data set that actually, I don't know if I need that. I think I ended up not using that. In any case, yeah, I didn't use that. Probably can delete that. Here we've got a histogram. The histogram is available here from the analysis toolkit. So I would just drag that in. And you need to plug in some things. So it's called, the block is called W sub S, the waiting time in system. Its title is histogram of that. And then you can see I'm grabbing from the time measure in. I'm just getting the distribution of the times. Also asking to get the PDF and the mean. And then for these two, I'm going to plot the utilization. So this was a little bit more involved. I needed to drag a histogram data object here. So this is the VAV util data, a little technical now. And then we associated a recorder with it, which every minute goes ahead and looks at whatever is in VAV util data. And you can see I'm recording it down here in this Java code. Okay, so it's just a small little snippet of Java. And then finally, this is a histogram object again, and it's pulling a histogram off of the VAV util data, which is captured. So what happens here is the utilization is changing. The recorder sort of snapshots that every minute, records it in VAV util data, and then you're building a histogram off of that. So this is just going to show us the distribution of the utilizations across time. This animation piece just shows arrivals. And then as the service is performed, you'll see the agents move across here. In the Mac versions, the image files are missing for some reason in the Mac version of the software. So you will see sort of like a little block. But on Windows machines, you should see the actual agents move. And what else? Yeah, we can observe the animation here if we want. A couple of other notes about this model that I think are important to sort of kickstart us is the randomness. We're going to have to do multiple runs of a model to sort of assess performance. And we can see that, I'm going to just show you where I've set this up. There's some other commitments also that I want to mention. There's preview, you know, where do I want this? I think it's in simulation main. Oh, run configuration. Yeah, so the model time, I'm limiting our stopping time to 10,000 minutes. What I'm looking to avoid is a situation where we generate more than 50,000 customers because we have a cap of that 50,000 because of the version of the software. So I want to avoid sort of reaching it. So I'm going to cap us at 10,000. And then what I think is also important is if I did multiple runs of this model, just going here, simulation main. So the model time is captured here again. Oh, 19,000, excuse me. I'm not sure which of those two is going to hold up. Well, maybe I should change this to 19,000 as well. But what I want to do is I want to ensure that each run comes with a random seed. So basically these random seeds are sort of starting points for random number generators. So if I were to repeat the simulation, I would get a different sequence of results. And the importance of this is, imagine showing up at this coffee shop on a particular day and observing it. Yes, you'd get good information, but it's possible that you may need to observe it multiple days to sort of get a fair sense of what performance looks like. And this randomizing of the seeds allows you to rerun the model and sort of get a different day, so to speak, to assess it. All right, so let's have a look at the base case. The base case is where I have 7 baristas, mean service times 150 seconds, standard deviations of 5 seconds because we're using jurors. In the queuing analysis, I discussed this model. We're going to analyze one barista in isolation. That one barista in isolation sees 22.43 customers per hour. Mean service time is 150, service time is 5. There's just one person, and this standard deviation is 5. This isn't really relevant because there are 0 VAVs currently in the model. Let's just make sure it runs. All right, so you're going to get sort of a compile and a build there, and it pops up a window for us like this. I want to just show you a couple things here. So the model is actually, is it going? Yeah, it is going. But I want to click on this little gear, and it actually ran to completion. All right, so let's try this again. Stop it, and I'll run it. You can see it running here, and it's running pretty fast, actually. Quite sure why it's that fast. So let's just slow it down. All right, so it's now running much slower. You can see the agents queuing up here and going through the process. Here's your distribution of waiting times. There are no VAVs in this model. You can confirm that there's no VAVs here. There's only one juror, and the arrival rate is 22.43. So this is a base case analysis of a barista in the base case, right? And you can see the distribution of the utilization is really tightly clustered in the 90s here. So I think what we discovered was going to just speed this up now, and it'll wrap up. It'll go to 19,000, and it just run it to completion. All right, so it's got a very large. This is expressed in minutes, 48.23. I think we had something like 20.38 in the queuing analysis, which is interesting. The variance, because our utilization is so high, is going to be relatively high, which is why we may need to simulate this being multiple times. So let me run it again for you. And I just did that. I clicked here on the stop, and I reran it. So I got an 1894 this time. That's that random seed at work, right? It's sort of kicking off our simulation process again. So multiple runs are going to be necessary to estimate your quantities if you're using the simulation, but it also brings some benefits. Now you're able to observe your distribution of the wait times, the distribution of the utilization. So some value added here. All right, we will look at our different scenarios in the next clip.